Okay. All right, so thank you everybody for coming. So today we're very happy to have James Watson, who's at the lights. Okay. Eight. Okay. Did that change? Yeah, so we're very happy to have James Watson, who is a postdoctoral scholar at the Joint Center for Quantum Information and Computer Science at the University of Maryland. And he's working at the interface between computer science, mathematics, and physics. His work focuses on tools from theoretical computer science to explore complex physical systems and the possible limitations. James received his PhD from the University College London in 2021. And we're very happy to listen to his talk on quantum algorithms for simulating nuclear effective field theories. So go ahead, James.
Awesome. Thank you so much for thanks so much for a lovely introduction, Dean. It's great being here and it's great to chat with you guys. As Dean kind of alluded to, I'm not really a nuclear physics guy, so I'm probably going to commit some horrible faux pas and say something I shouldn't about something in nuclear physics, and I'll know about it. So please correct me if I do. Yeah, so we're talking about quantum algorithms for simulating nuclear effective field theories. So these are algorithms running on a quantum computer to predict properties about or nuclear physics. So I thought I'd start with a summary. This is a QR code you should be able to scan and follow off on the paper if you want. So start with some motivation, talk a little bit about chiral effective field theories and quantum simulation, very brief overview of quantum simulation, and then talk a little bit about optimizing quantum simulation for chiral effective field theories and resource estimates for nuclear spectroscopy. Does the QR code work? Somebody's trying it there? Yeah. Awesome. Okay, it's meant to be an atomic nucleus. I'm not sure if we can out that one. So for a while now, over 50 years, I think, we've had this wonderful theory of the standard model and QCD, and we'd like to ideally be able to make predictions with it. I'd like to be able to predict and kind of answer lots of questions down here at the bottom. So
Yeah, maybe with more CSAT.
Hi, video cam?
Yeah, video cam.
Oh.
Hi. Yeah, I flip.
Oh yeah, okay, awesome. Yeah, so now you can see all the interesting questions that we're going to answer today, obviously. Yeah, so we're going to answer questions about the origin of heavy elements and dark matter and interactions with regular matter. But to get from at the top here, the standard model down to the questions at the bottom, there are a whole lot of intermediate steps that go through, using the standard model to predict nuclear and high nuclear interactions, come up with effective field theory forces, to then predict many body structures or atomic nuclei, and then answer these questions at the bottom. And the question that I think some people have asked, Dean and some of the others in the audience have asked, is can we use quantum computing and quantum simulation in particular to speed up or otherwise aid these kind of intermediate steps going from the top to bottom? And so really,
Click on the slide.
I'm going to click the slide again.
Yeah.
This is then many PowerPoint presentations. Yeah, so we want to go from our standard model through some sort of effective phenomenological model to get some information out about many body structure and reaction calculations, and eventually do some nuclear physics. And the question is, can we use quantum simulation or quantum computation to speed up any of this? So I'm told by eminent and smart people in the audience here that some of the things that we want to calculate in nuclear physics involve things like scattering cross sections, low-lying spectra of nuclei, lots of other interesting stuff like this. So if I want to perform one of these calculations, I want to stick it into my computer, my quantum computer, and we need a model of physics to simulate. I need put like a Hamiltonian or a Lagrangian into my computer, do some Monte Carlo, I get some numbers out, and these tell me things about my spectrum. So obviously the natural thing to do, if you're a naive person like me, is to go to QCD and you go, okay, can I try and simulate this from first principles? And I'm told that if you try and do this classically, you can just about get out the properties of deuterium using classical Monte Carlo. And quantumly, people have done some kind of resource estimates, how much or how many quantum gates on my quantum computer would I need to get some properties out of our simple quark transport properties. And the first estimates come to about 10 to 50 gates, which is wildly implausible, not just on a quantum computer, but a very, I think you can do this with a bunch of GPUs if you need to. And of course, the flip side of this is, we don't go from the ground up, we don't use QCD, but we use some kind of semi-empirical model. We use something like mean field theory. And of course, these models aren't always totally well justified. They're not totally reliable. It's hard to kind of talk about systematic error in these models. So the question is how or what kind of models do I want to choose to simulate my field sets. So I think I'm told that Weinberg in the 1990s came up with the idea of Sharrow effective field theory. So the idea being to take the most general possible regression, consistent with QCD and the approximate Sharrow symmetry, and then treat protons, neutrons, and pions as the effective degrees of freedom. So the model that I have in my mind is you have protons and neutrons moving around on lattice, if you discuss your lattice, and they exchange pions in directions. And of course, what you can do is you can consider terms in this Lagrangian up to a given order, given kind of momentum or energy scale, typically I think 140 MeV, and you get a kind of nice theory describing your nucleons and their interactions more relativistically. And treating the Lagrangian or the leading order terms for something like this, I'm not going to talk about this in any detail. I'm sure most of you in the audience know more about this than I do. I'm just going to kind of have like a vague term of expansion in my head that looks something like this, where I have some ordering of my terms in terms of an energy scale, starting with a contact interaction between my nucleons. And then the first order term being a single pion exchange, double pion exchanges, etc., etc. And we need to make a choice to truncate this expansion and how to express this expansion, etc. So now we have a model of nuclear physics, which is, I'm told theoretically well justified, and it's ideally simpler than QCD, so I'm not simulating all of QCD. The question is, what do I do with it? I've got, a Hamiltonian or a Lagrangian expressed in terms of the Sharrow effective field theory. And I want to know, is there anything I can do on a quantum computer that I might have some hope of speeding up performance using my quantum computer compared to a classical computer? Well, a key primitive, when we're looking at these things, for quantum computing, or a key primitive for both spectroscopy and scattering, is performing the time evolution of quantum state. So you just take your quantum state that you've gotten prepared somehow, and you want to time evolve it under the adjuvant Hamiltonian, just doing a unitary evolution of time. Classically, we know this occurs in the sign problem. We have these positive and negative amplitudes. They can interfere in a horrible way, and this induces the sign problem. And this kind of incurs huge resource costs if you're trying to do something like this using Monte Carlo. But on the other hand, quantumly, we don't have this problem. There's provably no sign problem. I can take my quantum state, I can time evolve it, and I can get out a kind of approximation to the final quantum state efficiently. And here I put efficiently in quotation marks because it might be efficient from a computer science perspective of not blowing up exponentially, but the resource costs that you need to actually do this might be prohibitive. And so the question that we're going to ask is, how feasible is quantum simulation of Sharrow effective field theory? So particularly if I try and implement a time evolution operator of my Sharrow effective field theory for a certain amount of time, characterized by, let's say I want to look at or resolve energy scales in my nucleus to a certain precision, what kind of resource costs do I need for my simulation of chiral vector field theory? Okay, so I'll talk a little bit about the work that we did, and then I'll actually explain the work that we did. So if you're interested in the paper and you want to zone out the rest of this talk, the kind of idea behind, or the kind of the final results of our work, is that we did these resource costs, these gate counts, for NISQ and fault-tolerant quantum computers, the task of time evolution spectroscopy of nuclei. So here, people know what the term NISQ means in this context? I'm getting some nods. Yeah, okay. Some shakes in the head. So NISQ is a noisy intermediate scale quantum device. So it's basically the kind of quantum devices we have at the moment. They kind of suck. We can't really do much with them. But the resource costs that or the kind of metrics they use for resource costs on NISQ devices are different to the resource costs and metrics they use for fully fault-tolerant quantum computers that we hope to have in the future. So you think, if I say NISQ at any point, you should think of kind of crappy, noisy quantum devices, whereas the fault-tolerant device is going to be a beautiful, perfect quantum computer that we should hopefully have in the near future. And we didn't just consider, a particular Hamiltonian or a particular formulation of these chiral vector field theories, and we looked at various orders of the expansion and different formulations of each of these terms. And then trying to characterize what the resource costs for these tasks are for each of these Hamiltonians. And in order to kind of characterize these results, we tried to kind of improve on or to try and implement these kind of state-of-the-art fermionic encodings, bosonic encodings, various different error analyses to kind of minimize the resource costs and determine what kind of scales are being feasible at. And this allows us to compare the efficiency of simulating leading order effective field theory Hamiltonians. Okay, so does anyone have any questions about anything I've said so far? Or okay, perfect. Everybody understood it perfectly. I'm very happy with this. So let's talk about the kind of primary object of study that I'm going to be talking about today, which is time evolution algorithms on my quantum computer. So, as I said, time evolution is an incredibly important primitive. In particular, relative to the task of quantum phase estimation, which is the algorithm I use to do spectroscopy on a quantum computer. Time evolution is really the kind of essential component. It's the hard and costly part of the evolution or the algorithm that I need to implement. So what we're going to do today, or what we're going to be looking at today, is product formula time evolution, or truncating, as you guys are probably at least familiar with that example. So the idea is I have a Hamiltonian. I can break it up into local terms. It's a sum of these local terms hj, where each of these, let's say hj's interact or represents a local interaction, like a Boole interaction or something like this. And then, of course, what I can do is I can take a sufficiently small timescale delta t, and I can approximate the full time evolution by, I can approximate the full Hamiltonian evolution by just a product of the simpler terms. And I'll call that my product formula unitary p for some time delta t. And we choose this decomposition such that these unitary operations that I have here, e to the I h1 delta t, these are going to be operations which are efficiently implementable on my quantum computer. So quantum computers can typically implement these unitaries very efficiently, and so we just choose our decomposition to make this a very efficient unitary to implement. And then it turns out, using Taylor expansions and whatnot, that this this approximation algorithm has an error that scales something like this. So if I take r steps of this approximation algorithm, I get an error scaling as r times delta t squared. And if you just run through some of the maths, it turns out you need a number of time steps or a number of kind of repeats of my truncating algorithm, my product formula algorithm, that scales as the overall time able to simulate divided by the error. And there are a bunch of other factors that have been hiding in this big O here. But for the moment, we're not going to be concerned about that. And I'll talk a little bit about it maybe a little bit later. So this algorithm is basically saying, if I want to time evolve my state for some Hamiltonian, I can get an epsilon good approximation to basically all properties of my state using this algorithm, provided I choose a large enough number of these repeat time steps. Okay, so at some point, if any of you kind of know anything about quantum computing beyond truncating, you'll probably come to me and go like, James, there are a huge number of these awesome other algorithms that we typically use for stuff like LCU, quantum signal processing. These are super hyped up algorithms. They perform better asymptotically. Why aren't we using them? And there are two reasons. I'll expand on this a little bit later, but the kind of fundamental idea is that although these algorithms often have asymptotically better performance, they lack a lot of very nice properties. In particular, if you actually go away and you kind of run these algorithms and see how they perform, but a particular time step and a particular Hamiltonian, their performance actually often worse. And they often don't have also very nice properties that this truncatation or product formula method have. So for example, truncatation incorporates a kind of commutator scaling, in the sense that if I have a Hamiltonian that's mostly a commuting Hamiltonian, I get better performance. It also inherently preserves locality. It doesn't require ancillary qubits, so I can kind of minimize my resource costs quite significantly. Okay, so that's, I think, all I'm going to say about the fundamentals of quantum algorithms, or the quantum algorithm that we'd be interested in. Does anyone have any kind of questions about that so far?
So in your broader extension, how do you choose the delta T? Like, how do you know what that is?
So yeah, that's just going to be, sorry, you're right, I haven't really explained it. So delta T here is just your overall timescale T divided by the number of steps R. So it's basically just a count of you want to make it. So you should think of this as like being T squared over R, and so if you power larger, some fixed time scale, I'm reducing that.
So this H commute,
Does H commute? No.
and does P factor that T?
Yes, so I'll talk about this later, but there's a fraction that we call alpha here. And alpha is going to how commuting is Hamiltonian. So if you have a non-commuting Hamiltonian, very non-commuting Hamiltonian, your errors or the number of times that you take is going to be larger. And you can kind of rigorously characterize that. Any others? Cool. Okay, so, sorry, was there somebody else's question? Okay, cool. So now I've talked to you about the quantum algorithm that we're going to use, and I've kind of alluded to the Schreier effective field theories. I'm just going to take you through a kind of like an optimization process for the simplest possible Schreier effective field theory, the pionless effective field theory. And so this is kind of like maybe the most boring part of the talk. So if you want to kind of just try and follow the vibe rather than the actual details, I'm not going to blame you. So pionless effective field theory is really going to be the kind of simplest possible Hamiltonian, or the simplest, like maybe interacting Hamiltonian that we can consider here. So we're basically going to ignore these kind of pion exchange terms and just focus on some contact interactions that occur between the nucleons. So the image you should have in your head is I have a Hamiltonian, and what I'm going to do is I'm going to discretize my spacetime in 3D. And at each point, I can have a new proton and a neutron, or a neutron that spin up or spin down. And we're going to choose to work in a second quantized formulation and a position space formulation. So I'm not going to be working in momentum space. And the Hamiltonian that we're going to, what this is going to look like, is basically going to be like a fancy Fermi hub. So on one hand, I'm going to have this kinetic energy term. So this is just the nearest neighbor hopping term between nearest neighbor sites on my lattice. And then I'm going to have a 2 local and a 3 local on-site interaction. So my neutrons or my protons on-site are going to interact with each other through this 2 and 3 body interaction. And kind of like, and I've also just realized I've missed a sigma index on this sum here, but this sigma index runs over the protons being spin up, spin down, neutrons spin up, spin down. So the kind of model that I have in my head when I'm working through this is I have a bunch of kind of spatial sites denoted by these black circles that form a lattice. And within each of these spatial sites, I have 4 possible fermionic modes that correspond to the spin up, the spin down protons and neutrons respectively. And they can do kind of nearest neighbor hopping between the lattice sites. And then within each lattice site, I have a 2-body and a 3-body interaction that interacts between various combinations of the protons and neutrons. And so it's a pretty basic model of some fundamental interactions. So it's a good place to start to see if we can optimize this and try and put this on our quantum computer in a resource efficient way. So what we want to do is we want to take advantage of as many details as possible of this Hamiltonian to do our quantum simulation task and speed up as much as possible. So if you look at the details of our quantum simulation algorithm, it turns out that by far the most expensive term to implement is the kinetic energy hopping term. So just this term, the kinetic energy, where I have a nearest neighbor hopping site between nucleons of the same type. So this is represented by this unitary operator, e to the I a dagger a. And the fundamental reason for this is something that I'm sure you're all familiar with, right? This hopping interaction is a hopping interaction between fermions. And fermions have this horrible property that if I exchange them, they pick up a negative sign in the wave function. And this has caused, I'm sure, a lot of frustration for people in the audience here in particular. So the question is, how do I simulate fermions? Well, in order to do that, I need something called a fermionic encoding. So basically, I need something which will replicate these exchange interactions for my fermions. And the most typical one that I'm probably some of you might have seen before is called the Jordan-Wigner mapping. So this takes this encodes my local creation or annihilation operator on a lattice with lattice dimension L in D dimensions with an operator that has size L to the power D minus 1. So this is a pretty big operator to deal with, and therefore it makes it very expensive to implement with a quantum computer. Big operators are expensive to implement. And there are alternatives to this, like the fast fermionic Fourier transforms, swap networks, given rotations, but I'm not going to go into that. So the actual kind of form of the operator, if I do this on a two-dimensional lattice, is just going to be a long chain of Z or Z operations, which string across my lattice in this big snake, followed by a this operation here, this X plus I1. And as I said, doing this whole big string of operations, this is expensive to implement. And so the hopping terms, if I actually kind of draw them on a lattice, look something like this. And again, this can have a kind of size, if you want, which is quite extensive. So what we'd like to be able to do is we'd like to be able to transform this into a more fine-grained or a more local interaction. And indeed, you can generate something like this. So what we can do is we can leverage the locality of our interactions, plus the fact that the number of fermions in our Hamiltonian is preserved. This is very important. And you can encode your fermions using a different encoding. In particular, there are two encodings that exist. Well, there are actually a lot more, but the two encodings we're going to look at are called the Strata-Dirac or the compact encodings. This allows us to implement these hopping operators in a constant amount of circuit depth. So we end up with a fermion encoding plus a Hamiltonian structure, which now allows us to kind of highly parallelize each step in our Trotter algorithm. And it allows us to implement each of these steps in order 1 depth. So independent of the number of particles I have, and independent of the size of my lattice that I'm working with. So this kinetic term that I have can be implemented just as a set of kind of like jump operators between nearest neighbor terms, kind of along each of the cardinal directions in my 2D lattice. So it's really just like an order 1 chunk of my quantum circuit. And in particular, what you see is that if I have n fermionic modes, then the circuit depth I require in terms of quantum gates goes from something scaled as m squared for the naive Jordan-Wigner encoding down to something that's an order 1, a gate depth of 128. So m here is just going to be the number of fermionic modes I require. So for a 10 by 10 by 10 lattice with 4 species, this is 4,000. So this is going to be order 16,000 at the top there. It's a pretty significant reduction. But we can actually even do better than this. I won't go into too much details, but if you look at this Hamiltonian a little bit closer, you'll notice that there's no mixing between different species. So I don't have protons going to neutrons or it's not going to spin down. Everything's going to preserve, the number of each species is preserved separately. And this allows us to actually do something even kind of clever. And we can encode each fermion as a separate fermion encoding. And so we're kind of encoding them individually in separate layers, and we're just going to stack those layers together. And this allows us to reduce our circuit depth even more. something that's kind of like significantly better at the expense of slightly more qubits.
So James,
Yes.
in the case where you're doing a few body system, let's say an alpha particle, where you only have one of each, then you can throw away all the anti-symmetrization completely, right? And then how cheap does it become?
So in that case, are you talking about the case where I have, when you say one of everything?
Oh, proton up, proton down. No, they're not two of any.
But you're still doing it on this lattice structure?
You're still on the lattice.
I don't think you actually get any savings in that case.
No,
So you still need to simulate each species separately. So you could switch to like the first quantization picture, in which case you would get some savings. You've got fewer particles. If I'm understanding you correctly.
But you could order it so that all the proton spin ups come first, then the proton spin downs come next, and then the proton and the neutron ups come next, and the neutron downs come next. And then there's no rearrangements. There's no permutations that swap because they only hop. You see what I'm saying? The dictionary ordering never changes.
Right, but in that case, wouldn't you have to be able to go from a spin? I don't know how you include the dimensionality of the lattice in that, if that makes sense.
You would have your L, you have your D. Sorry, I'm taking too long.
No, no.
You have your whole lattice here. You wind through your whole lattice that
Right.
for the proton up. Then you'd wind through your whole lattice for the proton down. It'd be 4 copies of the lattice, sort of.
Oh, and you're saying if you only have one particle for each of those?
Yeah.
Yeah, actually, I think you probably can do that. Yeah, because you're never changing the ordering, so I think that'd actually work. If you're doing a single particle.
Sure.
Yeah, actually, it's a nice idea.
And just, I have maybe a technical question on the VC encoding, the compact encoding. So is it basically like Jordan-Wigner, where you add these extra particles and maybe certain interactions, but then other than that, is it Jordan-Wigner, or is there something else going on?
Yeah, so the VC encoding is kind of like a fancy Jordan-Wigner. So you're adding these extra particles, but you also have this additional constraint that you have to restrict to a certain subspace. You have to prepare your state in a certain, these are series of qubits in a certain subspace. And that's what's allowing you to replicate the exchange statistics locally. That's kind of like, it's not almost a topological property, it's a topological property. It's kind of like a deformed Fourier code in some sense. And that's, you can think of the Fermat's excitations of that Fourier code.
Okay, and is that initial preparation challenging, or is it?
Yeah, that's a really good question. Maybe is a good question. It depends whether you're allowed to do measurement on your device. So if you can't do measurement, it becomes more expensive. If you can do measurement, you can prepare it in log time in the size of your lattice, or even constant time to be like. Yeah. So there is a state preparation step I've kind of ignored it. Sure. Okay, so I've talked a lot about using the structure of the Hamiltonian here to kind of speed up our quantum simulation. I'm going to talk a little bit more about the actual algorithms that we're using. So I alluded to somebody over here asked a question. What else my Hamiltonian is non-commuting? And the question, or the way that this comes into the kind of error in your algorithm, the number of the amount of resources that you need, is quantified by this quantity alpha. So the error, if I want my product formula, which I've repeated r times, to achieve a precision epsilon, I need a number of steps, so I need a number of product formula steps scaling as alpha t squared of epsilon, where alpha here is this sum of commutators between all the terms of my Hamiltonian. And the question is basically how can I characterize the error associated with this stuff. And what we're trying to do here is trying to do resource costs to get some kind of, I don't know, some information about how expensive implementing this algorithm is going to be on my quantum computer. So I'd like to be able to characterize what this quantity alpha is going to be. What is the kind of non-commutative properties of my Hamiltonian? And I won't go into any significant details here, but again, we can use the fact that the number of particles here is preserved by this Hamiltonian, or by this Hamiltonian evolution. And rather than using the spectral norm in this quantity here, we can actually kind of use some state-of-the-art stuff from this paper here and characterize this alpha quantity not in terms of the spectral norm of this commutator, but in terms of what's called the fermionic semi-norm, which characterizes it in terms of the number of particles or the number of fermions present on my lattice. Okay, so at this point you can go, James, this all sounds very fancy, but like if you've bored of the technical details, you want to zone back in, this is the kind of like more fluffy stuff that is less difficult to pay attention to. And so at this point you can go, James, this all sounds great, but are you making any real improvements on the resource cost set? I'd like to argue that, yeah, we are. So I've got some comparisons for different orders of Trotter formula. So these are just different formulations of this Trotter algorithm. And compared it to some previous Rogero. And you can see that his results are up here at the top. They're these blue dots. And you can see that our kind of resource estimates down here, are better by a factor of something of the order of about 10 to the 6 or 10 to the 8 in terms of the resource cost, which I think, or I'd argue, is a significant improvement. And so a little bit on the side here, you can actually talk about going to higher order product formula. So there are these p order product formulas, which scale with the resource cost out to this horrible thing here. It's awful, it sucks. And in particular, if you want to calculate the error associated with this, you want to use some resource costs, you have to calculate this absolutely disgusting nested commutator here. This is a super difficult thing to characterize. And indeed, we had to try and characterize this in the paper. If you scan the QR code area earlier, you go down to the appendix, we try and compute this there. So I'd like to very quickly advertise a new package, software package that we're writing up called Protomania, which is going to do exactly this computation for you. Hopefully that's going to be out sometime towards the end of the summer. Okay, so I've talked a lot about pionless effective field theories here, which is great, but they're very simple and arguably don't characterize a lot of important physics. So we'd like to go beyond pionless effective field theories and maybe include some of the physics of pions. And the question is, how expensive this is going to be. Is this going to totally be totally infeasible? Is it something that's going to be only a little bit more effort? What does this look like? So if you look at the term that you now have to add to your Hamiltonian or your Lagrangian, it looks something like this. You have like a kinetic pion term. You still have your nucleon terms with the contact interaction. And then you have the interaction terms between your nucleons and your pions. And this is meant to say, but what cost do we pay in simulating this? At the bottom here, that somehow messed up. And actually, when you look at this Lagrangian, it may not be, sorry, it wasn't totally obvious to me, but actually it turns out there are multiple different ways of simulating this on a lattice. There's the kind of obvious thing where you just you latticeize everything. You latticeize your fermions, your pion field, and then you just sort of replicate everything as it appears. So we call this the dynamical-pion case. But you can also look at the case where you remove the dynamics of the pion field, or sorry, not the dynamics, the time component of the derivative and the time component of the interaction. And you only simulate spatial dynamics. And this requires you to take multiple kind of Monte Carlo runs of your initialization of the pion field. But it is arguably or potentially a much cheaper way of simulating this. And then alternatively, you can integrate out your pions totally and instead replace them with an effective kind of Yukawa potential, which I've written here down at the bottom. Don't bother looking at it. All you really need to know is that it decays exponentially with the pion mass. And, again, these were big complicated expressions. If you want to have a model in your head, what does this look like? The dynamical pion case looks something like this. We have fermion sites here in black. The fermions can hop around on the lattice. We have pion sites in red. The pions, I guess, hop around on their lattice, and they can interact together on nearest neighbor sites. In the instantaneous pion case, the pions essentially aren't moving, and we're replicating that kind of the dynamics of the pions by sampling from basic Monte Carlo sampling from the action. But again, we have the fermions hopping around, and we have interactions between the pion field and the fermions. And then finally, we have the kind of Yukawa type potential where I've integrated out pions totally, and I've replaced them with a long-range interaction between nucleons. And then nucleons, or because this is an exponentially decaying interaction, you can think of just truncating the interaction at some finite distance and then implementing that. Okay, cool. Are there any questions about that? I probably can't answer them, but I'll try to. Hey.
It
the long-range interaction, nucleons can still hop around though, right?
Yeah, the nucleons are hopping around. Yeah, sorry, I didn't draw the arrows because I thought it would be too confusing, but yeah, nucleons are hopping around on the lattice. Sorry, was that a question or just a scratch? Got it. Anybody else? Okay, cool. And so hopefully that makes some sense, it gives you some intuition. I don't expect you to like be thinking of the entire like Hamiltonian or Lagrangian that's happening here. Please don't. I'm certainly not. And you know, you can do all of that kind of optimization stuff that I talked about earlier, but now for these big models, or these more complicated models that I just introduced you. I'm not going to take you through that because honestly, that'd be boring as hell. But you just give you a kind of flavor. When you introduce these pion fields, there are a lot of kind of details that you have to work out. How to encode these scalar field theories with these fermionic interactions. There are a lot of kind of encoding schemes for this. And with that, with those encoding schemes, you have to talk about choosing a pion basis. You should talk about representing your field, your pion field as spin operators. And you choose cutoffs for your pion field and conjugate momentum. And in the case of the one-pion-exchange, so this is where you've got the Kawa type interaction, you need to determine the best possible or most friendly interaction given the fermionic encoding. Do things like look at the cutoff length for your interaction. And then for both or all these possible formulations, you need to talk about doing kind of circuit decompositions, Hamiltonian decompositions to make things as optimal as possible. It's like 80 pages of work in an appendix somewhere. Like if you really want to go through it, you know, be my guest. And so at this point, I'm going to present just like kind of the main work or the main results from the paper. And look at, you know, how feasible is this stuff on a quantum computer. So this is going to be the resource estimates you need to do quantum phase estimation using the P equals 1 product formula, so this truncating stuff I talked about earlier, to get a 1 MeV precision estimate for on a lattice with 6 fermions on a 10 by 10 lattice, 10 by 10 by 10 lattice with a correctness probability of 0.3. That's kind of arbitrary, and changing that correctness probability doesn't change much. And we're going to characterize the error or the resource cost in 2 metrics. So the 2 qubit gate depth. So you can think of this as kind of like raw circuit depth or the kind of number of computations I need for my computer or my quantum computer. So this is kind of maybe the most relevant metric for a NISQ device, these noisy quantum devices I've talked about. They can only perform very short circuits. So this is maybe what the most relevant metric here. The second column is going to contain the T-gate costs. So for a fully fault-tolerant quantum computer, the most important or the hardest to implement operation is something called a T-gate. And T-gates for various reasons are hard to implement. So this is going to be the metric by which we cost or do our resource costs for fully fault-tolerant quantum computers. Okay, so if you want all these guarantees, what kind of resource costs are we looking at? Well, for the simplest effective field theory, we're looking at about 10 to the 7, going down to about 10 to the 38, the dynamical-pion case. And I mentioned earlier that in the instantaneous pion case, we have to sample from the pion field multiple times. So this is kind of, I don't know how to put it, this is for like one run. This is not taking into account the overhead you incur from doing this Monte Carlo software. And then the T-gate costs are going to look something like 10 to the 14 to 10 to the 40. And on the right here, this column here expresses the amount of time that an ion trap quantum computer would take to run this procedure and still out this many T-gates. So this is pretty pessimistic, and you should be very upset about this. I certainly am. And in particular, I haven't even considered some of the state preparation overhead that would be included in this. So, you know, this is very upsetting. And, you know, you should be kind of very, or hopefully aware that these NISQ devices that we have at the moment, they have circuit depths which are well below these factors here. And I just put at the top here, if you use a slightly different version of the truncating, you can reduce the circuit depths and T-gate costs by a factor of about 10 to the 2. Okay, so that's a bit of a doozy. And this is basically a graph showing the same thing. The dynamical-pion starts way up here. The pionless starts way down here. And you can look at the asymptotic scaling, and I probably don't want to go into this too much. You can also characterize the error and the resource cost in terms of the actual asymptotic scaling, in terms of the number of fermions that you're interested in, the energy scales, the lattice size, precision, etc. So yeah, the conclusion of this part of the talk is, basically without major improvements to hardware or algorithms, spectroscopy of nuclear physics using this formulation is pretty dire. You can look at these models and you can compare which one is going to be better for you, but realistically, none of them beyond this pionless effective field theory are really feasible, at least according to these estimates. Yeah, so in summary, we examined the task of time evolution of spectroscopy for these four Sharrow effective field theories, or four formulations of it. And for the pionless effective field theory model, at least, utilizing the details of the Hamiltonian has allowed us to achieve resource costs, which are order of 10 to the 4 to 10 to the 6 better. We also provided the first quantum resource estimates for higher order terms in nuclear effective field theories. And we demonstrated a trade-off between different approximations to these terms. However, basically all of them are infeasible in the near and midterm. However, before I leave you on an incredibly pessimistic note, if I can change slide, I want to just kind of give you a flavor of what's happened in the field of quantum computing recently. So I gave you these very pessimistic estimates. And a couple of years ago, in 2018, some people did some estimates for things like the Fermi-Hubbard model. We love the Fermi-Hubbard model, it's so simple. But according to the kind of like estimates of the day in 2018, if you try to simulate the Fermi-Hubbard model, we tried to do some kind of quantum simulation tasks similar to what we were doing here, you need a gate count or a circuit depth of about 1 million. But successive improvements to algorithms, to basically to algorithms, people have brought this down to something that's closer to about 300, which is obviously much more feasible on a quantum computer. And so hopefully we can do the same here. And hopefully we can bring down our estimates from being 10 to the 9, or in some cases 10 to the 50, and put it in a much more reasonable kind of regime that we might be able to tackle in the maybe not near term, but the nearer term. So I thought I'd list some of these kind of improvements or potential routes to improvements. So the first thing is, you can write down your quantum circuits, and a lot of people have had a lot of success by basically just applying a machine learning algorithm to optimize the circuits, canceling out redundant gates where they appear, and kind of bringing down the overhead. In some cases, you can get an error reduction or a resource reduction by a factor of about 100. You can talk about using non-standard gates or non-standard gate decompositions in your quantum computer. You can look at new fermionic encodings, which drastically or can drastically reduce the resource costs, which I think is sort of given here. They've reduced it from like here to here. You can talk about different or better estimations for doing spectroscopy and quantum phase estimation. And a kind of very simple thing to do, which is kind of hard, but you can just look at how the algorithm actually performs in practice, right? These are kind of analytic resource estimates given by algorithmic guarantees. But if I just take my quantum computer, I run it, I look at the empirical error that occurs, and I extrapolate, that's not a totally unreasonable metric for what my quantum computer might actually be doing in practice. And often, the empirical error is going to be 10 to the 2 or 10 to the 3 times smaller than your analytic error. And there are a lot of questions to ask about things like using different hardware models and looking at lower cost use cases rather than doing a full time evolution. And we can talk about things like error correction from fermionic encodings, using randomized or other Hamiltonian symmetries. And of course, we've considered Sharrow effective field theories in this work, but there are a whole range of models that we use to simulate nuclear physics, and it's definitely worth considering there. And so before I finish up, I'd just like to mention some of my other interests that might kind of overlap with your interests here. So I'm interested in quantum algorithms for time evolution, Gibbs state preparation, state preparation on a quantum computer, and basically anywhere that we can try and speed up on computers. So yeah, thank you very much, guys.
All right, thank you, James. Very, very nice talk. Are there questions from the audience here? Yeah.
So we left us with the pessimism view in this era. You're saying that there's maybe hope in the fault tolerant era, but maybe this is more of a statement that I hope you can repeat than a question. But some like quick back of the envelope math, if you took like a modern CPU and you assumed every gate in it was actually a quantum gate and it was running as fast as modern CPUs could possibly run, and you ran it for 30 years, you would only be up to about 10 to the 30 gate depth.
Right.
And I seriously doubt we'll ever have a fault tolerant quantum computer that can do that. But even with these improvements, you're saying that give, 10 to the 3 magnitude improvements on these things, it doesn't seem likely that we'll ever be able to do any of these EFTs.
Yeah, that's a really good point. So if I go back to some of the resource estimates here. So something like 10 to the 7 gate depth, or 10 to the 17, that's not totally outrageous to think you can improve that with, okay, even if I had a fully fault tolerant quantum computer and, I had some sort of parallelism or something like this, I think you could bring this down quite significantly. I'd also add that this while isn't a totally pessimistic estimate, this estimate at the time here is, I think it's probably been improved on already since the paper that I used to characterize this came out. But yeah, I think basically, particularly for like these two interactions down here, the one-pion-exchange and the pionless stuff, I think you're definitely capable of bringing these costs down to something that's less than 10 to the 10, if you work really hard. Maybe less optimistic on the one-pion-exchange stuff. The other thing I should add is this T-gate cost. This is like a non-parallel measure of quantum computing, right? This is like the number of gates you use anywhere in your quantum circuit. So if you can generate these T-gates in parallel, you can drastically reduce, like, I don't know, if you have like a bunch of if you have 1,000 T-gate factories, you can, in theory, knock 10 to the 3 off this as a resource metric or time scaling.
There's a question from online, from Som Pai. Do you choose the lattice such that it maps to the qubit arrangement? Will that help to make this cheaper?
Do you choose the lattice? So yeah, that's a really good question. We don't. This is kind of assuming you have ideal hardware, and so there's no difficulty mapping your theoretical qubits, the qubits that you'd like, onto your actual hardware. In reality, that's not necessarily going to be the case, and you might incur some overhead mapping your idealized lattice onto like IBM's hardware or something. And so, in reality, there'll actually be some additional overhead that is incurred because of that. We didn't include it because these are already pessimistic enough. So once you're going to start including the actual like mapping to the hardware, this becomes potentially even worse. But it should only be like a constant factor overhead. So it shouldn't really affect these resource estimates.
So James, I was wondering if you apply the same sort of cost estimates for quantum phase estimation for the Fermi-Hubbard model repulsive. Let's say we wanted to find the ground state for a 16 by 16 lattice, something's maybe 24 by 24 lattice, just beyond what we can do now. Yeah, how large would the computational cost be?
Yeah, that's a really good question. So if you're looking to do spectroscopy on something like that, I mean, the state of the art of the Fermi-Hubbard model, and this actually uses a lot of properties of the Fermi-Hubbard model itself.
Yeah.
I think if you want to do quantum phase estimation, I think it stands at about a 2 qubit gate depth. I want to say about 5,000.
Okay, that's what I was gonna guess.
Yeah, I think that's about right. So 5,000 10 to the 3, 10 to the 4. There's a 10 to the 3 gap here, and I think actually there's a lot you could do to bring this down to that kind of level, at least closer to that level, using those kind of methods. But yeah, it's not trivial. Okay,
But if it was a 3D Fermi-Hubbard model, it would be 10 to the...
Yeah, it'd be much closer to this.
Yeah. Okay.
So the dimensionality here is actually incurring a lot of the overhead, which is a consequence of the fact you have more complicated fermionic encoding, and you just have to simulate more terms in your Hamiltonian, basically.
So in dynamical pions, can you actually describe pion emission?
Yeah.
Yep.
Yeah, that's what the dynamical-pion would give you.
And then whether you encounter the normalization problem?
Yeah, so you would, as I understand it,
Yeah, your nucleon mass would be renormalized. You'd have all kinds of problems, but
yeah,
you would have dynamical-pions.
yeah. I should have mentioned that here. I don't think you'll actually want to simulate this dynamical-pion case that much. We just did it as maybe an exercise. Just once you've done instantaneous pion case, it doesn't take much more.
Okay.
Yeah, I'm actually kind of curious about the scaling, but especially how it relates to this. So, I was just, wondering if you could talk about it, and in particular, like, were there any features of the scaling that you think indicate, the maybe dramatic growth in costs associated with the dynamical pion?
Yeah, that's a really, really good question. So this is something that we really struggled with when doing these resource estimates. So when you're doing these resource estimates, I'll try and find the page for the efficiency of the algorithm itself. You end up with these nested commutators, all these commutators. And you have to take the norm of these commutators. And in order to take the norm of your pion field, you basically need to find some estimate for at a given energy, how likely is my pion field likely to reach this? So you're basically characterizing the norm of your pion field. And rigorously bounding that is really quite hard. So rigorously bounding that and accounting for the error that it introduces and everything is pretty hard. And you end up with pretty poor estimates. We expect them to be much better. Like if you just take like a simple harmonic oscillator and you treat that as like model scalar field theory, and then you do like some truncation and kind of compare the error, it's a lot better than you'd expect from our like theoretical estimates. So we think there's actually a huge amount of room for improvement there, just from kind of understanding the dynamics of like a scalar field theory on a computer better. I think people like Natalie Coe, people have probably done a lot of work towards understanding that. So yeah, that's another thing you can work with. So when I talk about our estimates being pessimistic, there are a whole bunch of reasons why they are pessimistic, but in particular the dynamical pions and introducing a kind of resource cutoff for the conjugate momentum in the pion scale field and accounting for the norms of those fields, is really incurring a lot of the overhead in our resource estimates.
Gotcha.
So you mentioned those numbers there, those are for a 10 by 10 by 10 lattice. Right?
Yeah.
What is that like the normal size for classical simulation?
A little bit small, but yeah, we've done simulations with 10 by 10 by 10.
So these were all with a fixed like energy precision, right? Of 1 MeV. I might be revealing my ignorance here, but is that a function of the lattice or a function like that precision? Does that come from the lattice or does that come from the fact that it's being solved with a quantum algorithm?
That's just an arbitrary thing we chose for our quantum algorithm. We just like, okay, we need to do some resource estimates, look at the characteristic energy scale, spectral gaps of like helium and stuff. What kind of energy do you want to resolve that to be able to see the gap? So we chose 1 MeV. So that's what's going on here. That's why we chose that. So it's really the precision you're setting your algorithm to in this case. But sorry, go on.
I was wondering if you have a sense of how these costs would then scale with that precision.
Yeah, great question. So the algorithm is basically, if you choose a Pth ordered Trotter formula, so we've mostly been working with P equals 1, the resource costs scale as 1 over epsilon per 1 P.
So the precision is then just the how many time steps essentially.
Yeah.
Okay.
Yeah, sure.
Yeah. So how about the scaling of the particle number?
Of the particle, yeah, exactly. Yeah. So eta here is the number of phonons you have in your lattice. So you can see the.
So how about if you only have 2 or 3 particles in a system? So what's the number to be units?
So the number of qubits is determined by the size of your lattice rather than the.
I mean, in this situation, I just want to say that if you reduce your particle number, is it possible to do some simulation now? I mean, on the device.
Yeah. So yes, in the sense that you can always just take a smaller lattice and you put 3 particles or whatever on your lattice, and then presumably that introduces some systematic error that Dean probably knows much better than I do, or definitely knows much better than I do. So whether that's an interesting thing to do, I don't really know. That's maybe something Dean is better equipped to ask. If you just want to take a small system and have 3 fermions hopping around on a lattice. Yeah, again, whether or not this is feasible at the moment depends on how big you want to make your lattice, but I'd argue probably just about if you take a very small toy model.
About this kind of encoding, I think from your talk, I think that maybe the most difficult part is to do the anti-symmetry, right?
And also the induction, if the induction has some holding term, that will cause some problem also, right? So what else, what kind of difficulty, would come from the induction to the Hamiltonian?
What kind of difficulty?
What kind of type of the induction will cause some difficulty to do this kind of?
Right, what kind of, yeah, okay, good question. So for the, are you talking about that makes the Jordan-Wigner good?
Yeah, something like that.
Yeah, so basically anything where you have a transfer of fermions on your lattice. So you, for the hopping term, you have you have an annihilation operator here, creation operation acting here. But basically anything which takes anything from one side to another. So if you have some sort of long range interaction, which is an annihilation here to here, you're gonna end up with the same problem.
So on the contact term, I mean, the local term will be fine. Right?
That's totally fine, yeah. So if you just had, yeah, as you said, if you just had these on-site terms, it would be totally fine to implement.
Yeah, whenever you hop, you cause problems. Probably the worst case is like the tensor force when you can flip the spins from down to up and then go from S wave to D wave. That's the problematic. Yeah. Are there other questions? Check them out. Other questions? If not, let's thank James once again. Thank you very much. Great.